What's up, guys? Today we're talking about more characteristics of polynomial graphs, and we're going to be talking about a few different kind of unrelated characteristics. So I have out here a list of just a few things to go with this graph. We're going to look for the domain, the range, and then the intervals of increase and decrease. Okay, and domain and range are things that you really have seen before. You probably have been seeing this since middle school, but it's one of those things that people always forget about, and so we have to go back and make sure you remember exactly what domain and range are. The domain is where the graph is located in the x direction. That's one way of thinking about it. There's also a more numerical way to think about it. It's the values of x that you could plug into a function and get some kind of answer. So if I go to the left and to the right, where does the graph exist? Can I move my pen far enough to the left that the graph isn't there? Well, we know this is going to continue upwards and to the left forever, and this is going to continue upwards and to the right forever. So it is going to go left and right forever, which means I can't move my pen far enough to the left that the graph isn't there, or far enough to the right. Anywhere I go, left and right, the graph is there somewhere. Okay? That means the domain is from negative infinity to positive infinity, or another way of writing it is just to say all real numbers, and I like to use this little symbol. You could also say negative infinity is less than x is less than infinity. And this is just using inequality notation to say that x is everything from negative infinity to infinity. You could also say like this, from negative infinity to infinity, using interval notation. Okay, interval notation, inequality notation. I just like to use the symbol if it's all real numbers. Now here's the thing about polynomials. All polynomials have domains of all real numbers. So that means when you get the question, what's the domain of this graph? If it's a polynomial, all real numbers every time. They're always going to go to the left and to the right forever. They're never going to have a gap in the middle where you can't plug something in. You can plug any number you want into a polynomial and you will get some type of real number answer. So what about the range? Same thing as we did with domain, except we're going to talk about, instead of x, we're talking about y. So as I move my pen up and down, where does this graph exist? Well, it's going to go up forever. So I can, there's no point I can move my pen up to where the graph's not going to be there. But what about when I go down? You see there's an absolute minimum here, which means below that you're not going to have any graph. The graph's never going to go down here. So the minimum of the graph looks like it's going to be 1, 2, 3. In fact, this point looks like the point 2, negative 3. Let's write that out. So if I were to plug in every possible value I could into this graph, what types of answers would I get? What would be the range of the outputs, which is why we call it range? What are the range of outputs I can get? I can get a number as big as I want, but I can only go as low as negative 3. The graph will never output anything less than negative 3. So the range of outputs, the range of y values, will be from negative 3 to infinity. So you can use interval notation like this, or you can use inequality notation. I prefer the inequality notation, so we just say for the range, y has to be, now it does look like it actually includes that point. It actually does hit the negative 3, so I'm going to say greater than or equal to negative 3. If you prefer the interval notation, you can say negative 3 to infinity, saying y is going to go from negative 3 up to infinity. Either way is fine. Okay, so now we got to talk about the interval of increase and interval of decrease. Before I do that, you got to make sure you understand how we talk about locations on a graph. You don't usually describe a graph by its y coordinates. I like the example of saying it's like saying your address is 106. And that's all. You don't tell them a street, you don't tell them a city, you don't tell them anything. Well, 106 is not unique. There's a lot of people that live at the address 106. Okay, so we need to give a unique identifier for a location. And for graphs, if we're talking about a function, that's going to be the x coordinate. The x coordinate is unique. There's only one place on the graph where, for example, where x is 2. If I go over here where x is 2, go down to where the graph is, there's only one place there. There will never be two. For example, you can't have the graph here and also up here. It can only be at one place because of that vertical line test you learned about earlier. It can only cross through the graph once. So at any given x-coordinate, the graph can only be at one specific place. So when we talk about locations in a graph, we always use the x-coordinates to describe them. If I were to use a y-coordinate, say, yeah, let's go to that place where the y-coordinate is 1. Well, where does that happen? Because here's y equals 1 right here, right? That happens here, and that also happens somewhere over here. So how do I know which one you're talking about? You don't. So for unique locations on a graph, we always use the x-coordinate. We're going to describe the graph in terms of x. Now, intervals of increase and decrease simply mean where's the graph increasing as I read it left to right. If I were writing this like a roller coaster, am I going uphill or downhill? Right here, I'm going downhill. And I'm going to hit that minimum, and I'm going to start going uphill. So this is an interval of increase. Until we get to that maximum, from here to here, the graph is increasing. Then it's going to be decreasing until I get to that next minimum. And then it's going to be increasing forever. What you should realize is that the intervals of increase and decrease are going to be bounded by the relative minimums and maximums, or in this case, an absolute minimum. So we should go ahead and point out where those points are. That's a maximum, that's a minimum, both relative, and that's an absolute minimum. What are the coordinates of these points? This point looks like -1, 2. And this point looks like 0, 3. So how many intervals of increase or decrease do I have? I've got an interval of decrease from -infinity to this point. I've got an interval of increase between these 2 points. Then I've got an interval of decrease between these 2 points. And then an interval of increase from this point to infinity. Again, we only care about the x-coordinates. We only care about the things you would plug in to the graph, which is x. If I were to, into the function. So if I were to plug in a -1, I would get a 2 in the function. If I were to plug in a 0, I'd get a 3. If I plug in 2, I'd get a -3. These coordinate pairs, remember, are inputs and outputs for the graph. We only care about the inputs. So let's look at the intervals of increase. We've got 1 here, and we've got 1 here. That's it. So for the first interval of increase, remember, we only talk about the x-coordinate. It's increasing when x is -1 up to 0. So between -1 and 0 for x, the graph is increasing. So you can write out inequality notation. You'll say from -1 less than or equal to x less than or equal to 0, the graph is increasing. If you were to use interval notation, that would look like this. And again, I'm okay with either one, whichever notation you like the best, that is fine with me. I have reasons for preferring not to use interval notation, but we can talk about that later. Now, how do we say this one? It goes from 2 and it goes to the right forever. So it goes from 2 to infinity. So all I got to do is say where x is greater than or equal to 2. It's increasing. If you were to use interval notation, you can say from 2 up to infinity. So these are the same, these are the same, whichever way you prefer. Draw the line, separate these out. Okay, so intervals of decrease. This is going to go from -infinity down to -1. So anywhere that x is less than or equal to -1. That's just saying anything over here, this direction, less than -1. If we're using interval notation, from -infinity to -1. And then we have an interval of decrease right here from 0 to 2. Remember, we only look at the x-coordinate. From 0 to 2, the graph is decreasing. So we're going to say from 0 less than or equal to x less than or equal to 2, or interval notation. And those would be the intervals of increase and decrease. Okay, so real quickly, we're going to talk about even functions and odd functions. And it's important to note that I'm not saying even degree functions or odd degree functions. I'm not just talking about the highest exponent. If I say an even degree function, I mean it has a degree, a highest exponent that's even. What we're talking about here with an even function is one where all terms have an even power of x. All terms, not just the highest term. And odd functions are where all terms have an odd power of x. there's a couple things that comes out of that, okay? If you have an even function where all the terms have an even power of x, for example, here's a polynomial that's even. It has x to the 6th, x to the 4th, x squared, and it has a constant, which if you remember, a constant is actually x to the 0, and 0 is an even number. I intentionally put odd coefficients on here just to throw you off because I want you to know that the odd coefficients don't matter. All we're talking about are the exponents, 6, 4, 2, and that's 0 because it's x to the 0. It's the exponents of x. The exponents of x. All right, so when that happens, what you get is a graph which is symmetrical across the y-axis. That means it's mirror imaged across the y-axis. The part on the right, if you reflected it across the axis, it would map onto the part on the left and vice versa. And you can see in both of these examples that is the case. Okay, so in odd functions, here's an example. Again, I put even coefficients just to make you understand. It's the exponents. We're looking at 5, 3, and this is x to the first. Okay. Notably, what this means is that an odd function cannot have a constant at the end because a constant would have a 0 degree, an x to the 0 at the end. So their symmetry is a little different. They have rotational symmetry around the origin. That means if you take this graph and rotate it 180 degrees, just rotate it a half turn, it will map onto itself. The same with this one. Around that origin, if you rotate it a half turn, it's going to map right back onto itself. That's an odd function.